Hi, Shalom. I'm Professor Amos Agnon from the Hebrew University, and I visit the Ashkelon excavation in order to sample material that has been fired during a very precise time window, a month, 604 before Common Era, the month of Kislev or December. This is very unusual for us, but I'll explain first what we are after. So we are trying to reconstruct the variation of the magnetic field of the Earth, and the magnetic field of the Earth, we can measure it. Everybody can very simply, just by a compass like this. If you hold the compass, make sure that it's horizontal using this bubble here. Right, or plane, and then there's a needle that points to the north, right? And you can take your bearing with this compass. And the truth of the matter is that the north is changing with time. Since we have been measuring the human race in the last 3,000 years, we see changes in places, changes by up to tens of degrees. It's a small change, and if you note on your navigation charts, there's always the rate of change of the north. So you have the year and you have to calculate how much it changed. The reason for the change is very complex. The magnetic field of the Earth comes from the core of the Earth. So we go down there about 3,000 kilometers into the molten iron part of the Earth. I'm a geologist, and this is my origin is from down there. And this molten core is convecting over time. This convection creates a pattern that is largely like a dipole, but there are some components that are non-dipole. I don't want to go deep into that, but the bottom line is that when you stand on the surface of the Earth, you can see variations in the field if you wait long enough. Now, the variation is in the direction of the north, but if you hold that needle in a fashion like this, you can also see that there is an inclination of the field. So if north is there, we're in the northern hemisphere, typically the inclination is down. And if you stand on the North Pole, the inclination is 90 degrees down. If you're on the equator, it's horizontal. It also should help archaeologists, once we have these curves of change in time of the declination and the inclination, we also, we come to a site, we can only measure declination and inclination of something that has been fired and cooled in situ. Then we can tell the archaeologists that probably it's from this period to this period. I mean, it gives you some bounds.
So what do you hope to learn about by taking these magnetism fields? When you're working in our Tabun, what do you hope to find out by taking these samples?
We hope to find out where was the north during the year 604. Maybe it's not so, one should wonder why they talk about 604, but the thing is that the curves that we generate from many sites all over the country and all over the world, these curves have two types of data in them, the magnetic data versus the time. And very often in archaeology as well as in geology, the error, the uncertainty, the time is huge or big or whatever. Here we have a case where the uncertainty is very small, 1 month. And we actually are trying, we also collected some sample for pollen to verify that we're really looking on winter, because hoping to be able to identify the pollen grains that were captured in the tabun after it cooled and before the collapse, they should point at the winter blooming, which is not very strong here. So to answer your question, we'd like to get these 3 sets of data. Where did the north point? What inclination? How strong it was? And then we can compare it to other places, to other sites that have been hit by Nebuchadnezzar during his campaign or nearby. During that time, we had several campaigns largely from the north, Tiglat-Pileser and Sanherib, and so we can see how the field has changed from one campaign to another. And we do see already changes over a time scale of tens of years, of decades that we can resolve. So the bottom line is we'd like to be able to give archaeologists a tool to constrain the dates when you don't have an independent tool for constraining the dates.